Welcome back, students. In this video, we are starting a new lesson number 10, wave optics. In lesson number 9, ray optics, we studied light as a set of rays. But in this lesson, we are going to study light as a wave. For a very long time, people thought that light was a particle. The particle nature of light was fairly established. It was René Descartes, a brilliant French mathematician who lived in the 17th century, who first proved Snell's law of refraction using the corpuscular theory of light. Corpuscular theory meaning that light travels as corpuscles, like as particles. And he was the first person to do it. And the fallout of that proof was this, that light, if it travels as particles, then it should travel faster in a denser medium than the rarer medium. So light should travel faster in water than in air. But that is not the case, and people knew it then. So it was one of the criticisms of the corpuscular theory of light. But then, nevertheless, they accepted it because it made sense to people in many ways, and you could explain a lot of phenomena with the corpuscular theory of light. So it carried on, and particularly because of its support given by Newton. So actually, in the later part of the 17th century, somewhere around 1680s, there was a Dutch physicist, Christian Huygens, who proposed the wave theory of light, but it wasn't taken seriously because Newton was a great supporter of the corpuscular theory of light. In fact, he was such a great supporter that the corpuscular theory of light is credited to Newton and not to Descartes or anybody else. People generally think that it was Newton who proposed the corpuscular theory of light, but it wasn't Newton who did that first, it was Descartes. But then it is known to be a brainchild, it is understood to be a brainchild of Isaac Newton. But the corpuscular theory was not his invention. As he just said, Christian Huygens was a physicist who put forward this wave theory of light, but it wasn't taken seriously because of the reputation of Newton. Because Newton was considered rightly to be the greatest physicist then, and his support was to the corpuscular theory of light, and nobody really wanted to think beyond what Newton thought. So Huygens' wave theory was not considered for a very, very long time. But only after Young's double slit experiment, which we'll study in this lesson a little later, which conclusively proved that light is of wave nature, that people started looking at it very seriously, the wave theory of light. And Maxwell's equations finally proved beyond doubt that light is of wave nature. But the modern idea is not that. The modern idea of light is that it has dual nature. It's both a wave and a particle. And this is something that you dealt with in the lesson on dual nature. So what acts as a particle can also act as a wave, and what acts as a wave can also act as a particle, is how we understand light now. But in this lesson, we would be studying light as a wave. We would be studying about Huygens theory, Huygens principle, which tells us how light travels as a wave, and using that wave theory, we will prove the laws of reflection and refraction, and then we'll also be dealing with interference. It's a phenomenon which is actually the fallout of the superposition principle of waves. And we'll also talk about diffraction, which is interference involving many waves. There is also polarization of light, because light is a transverse wave, and a polarization can happen only for transverse waves. But that part we are not going to deal with, even though it is there in your textbook. It has been taken out of your syllabus by CBSE now, so we will not be dealing with the polarization of light. So we would be basically focusing on Huygens principle, which tells us how light travels as a wave, then the law of reflection and the law of refraction using the wave theory, and interference of light and diffraction of light. These are the things we will be dealing with in this lesson. With this introduction, we will get on to do what is to be done. Let's start with the idea of what a wave is. A wave is a disturbance that travels in a medium. If you drop a stone in water, then that disturbance travels in all directions on the surface of the water. And when I speak to you, then there is this disturbance that takes place in the air medium, and that travels in the medium and reaches your ears. And when you see the Mexican wave on a cricket stadium, the wave travels through the people or the medium there. So a wave requires a medium, except the light wave, because we said in the case of a light wave, the space itself is like a medium. So a wave is a disturbance that travels in a medium. And when we talk about wave, we talk about what is called as a wave front. Like when you drop a stone in water, you see circles around that stone. So the circle travels, it becomes bigger and bigger and bigger, and then travels from one point to all the points on the surface of the water. But at any one point in time, if you look at it, if you just take a photograph and then freeze it, then you can see circles. So what it means is that the points on the circle, they have the same value. Okay? They're either the peak or the valley or something in between. But if you draw a circle, then that circle, all the points on the circle will have the same value of the disturbance. We say that all the points are in phase on that circle. So the locus of these points is called as a wavefront. So this circle is going to be called as a wavefront if you talk about the water wave. And if you take a light source, then if you take a point source, then light will travel in all directions. So at equal distance from the point source, the sphere, the imaginary sphere, and all the points on that sphere will be in phase. So you can call that as a spherical wavefront. So you have a point source of light, and light travels from that point source, and at any distance you can form a sphere, and that's called as a wavefront. So a wavefront is a surface on which all points are in phase. All points will have the same value. Because if you take a wave if you take a sinusoidal oscillation, and in phase means that 2 points have the same value. So if one has a sine 30, the other will also have a sine 30. If one has a sine 45, the other will also have a sine 45. So that is why you say all points on a wavefront are in phase, meaning all points have the same value. So they have to necessarily form a circle if it is a surface, like a water surface, a plane surface, or a sphere if it is a three-dimensional wave, like a light wave. So you know what a wave is, you know what a wavefront is. Let me just try to draw it. So if this is the disturbance, this is the source from where the wave originates, then you can see circles like that. Okay. So this, all the points on this circle are they make a wavefront. So that is understandable because in the medium the wave will travel with the same speed in all directions. If you think about it, so it will cover the same distance here in a particular time. So all the points on the circle will be in phase anyway. They'll have the same value. If this is from here to here, if there is some distance r, if this is at one value, and clearly the disturbance will have traveled to this distance in the same time, and this value must be the same as this value. So all the points on the wavefront will have the same value. You say that all the points on the wavefront are in phase. Okay. So this is a wavefront. So you have this is actually a circular wavefront, the water wavefront. Okay. And if you take a point source, then you can have a spherical wavefront, like with the three-dimensional wave. If the light travels in space in all 3 dimensions, then you will have a spherical wavefront. And if you go farther away from the source, notice, then this will become flatter and flatter and flatter. Then at a far off distance, and you can expect this wave to become bigger and bigger and bigger. Notice that it's becoming flatter and flatter and flatter. Then you can say at a far off distance, you can expect the wavefront to be parallel. Okay? So now you see these circles are actually the wavefronts. Let me just draw one more. Okay, so it's like this. So this is a wavefront, another wavefront, another wavefront, another wavefront. So the wavefront travels in the medium. So the far off place, then though this appears curved here, but it's less curved than this one, and this will be less curved than this, and this will be even less curved than that. And the far off place, then it will look like a plane wave, be kind of parallel to each other. So then we call these as plane wavefronts. So this is a wavefront. So this is the source of the wave, and this is a wavefront. Okay. Okay, once we understand this, we will move on to talk about Huygens principle. Christian Huygens was a Dutch physicist, and then he gave us his theory of how a wave propagated in the medium. He said all the points on a wavefront behave like secondary sources. So you have a primary source from where light has emanated, and then say at a particular point in time when you look at it, this has a wavefront. What he said is that on this wavefront, all the points behave like secondary sources. So they have their own wavelets. What is a wavelet? A wavelet is a small wave, like a booklet. A booklet is a small book. A piglet, a small pig. The child of a pig, it's piglet. So we said each point on a wavefront behaves like a secondary source and gives out its own light. It produces its own wave. You call that as a wavelet. And if I draw a common tangent that connects all these wavelets, then that common tangent is the new wavefront. I want you to understand this. So, when you look at wave propagation at any point in time, you will have wavefront. Then from that wavefront, how do you go to the next wavefront? So he said all the points on the wavefront behave like secondary sources. And then they produce their own wavelets. And if you draw a common tangent to all those wavelets, then you get the new wavefront. Let me draw it. Let's say this is the source, and when you look at it, at time is equal to 0, at this time is equal to 0 is, that is when you observe, right? So this is a wavefront, so this is time is equal to 0, and the wave travels with speed v in the medium. So v is the speed of the wave in the medium. I told you that the speed of the wave depends only on the medium, not on the source. When I speak, I may have a different frequency from yours, but my sound wave travels with the same speed as your sound wave in the medium. In this case, it's air. I cannot control that speed. I can only control the frequency. You control your frequency. But the speed is not controlled by the source. The speed of propagation depends only on the medium. But for light, you don't need a medium. The space itself acts like a medium, if you want to call it that. Light doesn't require a medium, but this is how the speed is determined. Okay? The speed of a wave depends only on the medium. So likewise, here, when I start observing at time is equal to 0, this is the wavefront I got. And this wavefront will have many points. But I'm going to choose, say, maybe 1, 2, then 3, 4 points. These points are going to act as secondary wavelets, secondary sources. This is a primary source, and these points are going to act as secondary sources, and they will produce their own wavelets. Note here, these are not the only points. Every point on the wavefront will behave like this, but I'm going to choose a particular set of points, 1, 2, 3, 4. Okay, so let's say at time is equal to t, when time is equal to 2 from here, then this wave should travel a certain distance, and that distance d is equal to v2. So what happens is that this secondary wavelet of this point, it would have gone like this. It's not very clear. Like this. So you can see that this is a wavelet for the source. This is another wavelet, third wavelet, fourth wavelet, and not just these 4 points. All the points will produce wavelets like this. So what I'm going to do is I'm going to draw a common tangent, a tangent which is common to all of them. So what will happen is that that tangent will touch all these things now. Okay. Now this will be the new wavefront. So this is the old wavefront, this is the new wavefront. Okay, this is wavefront old, this is wavefront new at times equal to 2. And if this time changes to something else, then all the points here will behave like secondary sources and they will produce their own wavelets. Now you may get a third wavefront. So this may produce this wavelet, this may produce this wavelet, this wavelet, and I must be able to join them. Okay. So that would be the third word. So this is how wave propagates in the medium, and this is what is called as the Huygens principle. Principle of wave propagation. Okay. So you may ask, why should the wave only travel in this direction? This is a point source, then there would, as like this, if you take this point source, the primary source, wave is like here, and there will also be, the wavefront will not stop with it, right? The wavefront will continue. The wavefront would be here too, right? It travels all directions. Likewise, if this is going to act like a point source, secondary source, then why would it travel in one direction and the wave will also travel in the other direction? Right? It should travel in this direction too. Okay? And this one, like that, like that. So what happens to this? This side. Well, this cannot be explained very easily as we do here, but if you treat the subject rigorously, a rigorous treatment of this will tell you that you can ignore the back waves. The back waves will be immaterial. So the rigorous wave theory treatment of this concludes that you can ignore the back waves. You focus only on the front waves. Okay. So that's what it is. So you ignore this part. So you ignore this part. Ignore this one, the back wave, and focus only on the front wave. Okay. So to summarize again, Huygens said this. Each point on a wavefront behaves like a secondary source and produces its own wavelet. And a common tangent to all these wavelets will form the new wavefront. I hope you understand this. So we've done the propagation of wave for a spherical wave. So what will happen if you do the same thing for a plane wave? Well, this will be a plane wavefront. The plane wavefront will be straight like that. Okay? Because you can imagine a big circle. Because the plane wavefront you will see at very long distances from the source. So this is how it is. And then the next front would also be like this. Right? So from this point, you will draw this stuff. This will have this one, and maybe like if you take this one, and that will have this stuff. So you see, and if you draw a common tangent, take this point, something like this point, you see, something like this. So if you draw a common tangent, then you get the new wavefront. So for this also, you do the same thing. Like if you take this point, let's say, this is the wavefront, and this will be the wavefront. this will be wavefront, something like this. So then a common tangent will give you the next wavefront. So the plane waves will also travel like this. I mean, if the idea is the same for all wavefronts, you can see that the plane waves travel like this, straight like that. Okay, so this is the same as the spherical waves. Okay. The same principle is used here also. Now let me talk about how to derive the law of refraction using this wave propagation, Huygens principle. Let's say like I have the interface, the medium 1 and medium 2. I have an interface like this. Okay. Let's say I have an interface like this. This is medium 1 and then here it is medium 2. And let's say that I have a plane wavefront coming and hitting here on this side. From the light travels from this medium and then hits here. Let's see what happens now. So the velocity of light in this is v1 and velocity of light in this is v2. Let's suppose that I have a plane wavefront. Okay, in this. Okay. So it comes like this. This is a plane. Comes and hits like that. Okay, the wave light travels like this. There's a beam of light that is hitting here. And clearly this would be the normal, right? This would be normal. So this would be the incident angle. Let's see. If I take this, you see the plane comes here, comes here, comes here, comes here, comes here. And notice that when it hits this surface, this point is making contact with that surface, right? Okay, so beyond that, like this. Okay, so the wavefront, the wave is coming here, and the wavefront makes contact with the surface here. Now, this will act as a secondary source, and this will act as another secondary source, and this will act as another secondary source, another secondary source, another secondary source, secondary source, like that. You have innumerable secondary sources on the wavefront. But then look here, this source, the wavelet that this produces, it has to travel in the second medium. But here, not so. Here, not so. Here, not so. They will still, the wavelets that these points produce will still be traveling in this medium, the first medium. And this point source will produce a wavelet that will travel for a much longer time in the first medium. This will immediately start sending the wavelet will travel in the second medium. For this one, I'll call this as A, and maybe I'll call this as B, and yeah, this goes straight, right? So if you see, then I'll call this as C. So the wavelet that point B produces will travel in the first medium for the longest time. All the other points will travel for some distance in the first medium, and will start traveling a different distance here in the second medium, because the velocity will be different here, right? V2 is the velocity, V1 is the velocity in the first one. Okay, but then this point A will immediately, as soon as we hit here, the wavefront hits here, this point will be sending a wavelet into the second medium. Okay. So let us suppose that it takes time tau for this to reach here, for B to reach C. So what is BC? So BC is equal to V1 into tau. Yeah? So BC is equal to V1 into tau. It takes tau time for this wavelet to reach here. Okay? You can even draw it like this if you want. Let me just try to do it this way. Something like this. So V1 into tau is BC. But in the same time, what is the distance that A would have covered in the second medium? Let's assume that V1 is greater than V2. If V1 is greater than V2, in the same time B takes to reach C, A would have reached another point. But at that point, that distance would be V2 into the same time, tau, right? So, which would be smaller than this. If this was it, and this would be smaller than that. This was it, and that must be smaller than this. This is smaller than this distance. I want you to understand that. Okay? And what would this do? Well, this would travel into the first medium for a certain amount of time, and then it would have started traveling in the second medium. But this time and this time would be equal to tau for this one. I'll call this as K. This would travel tau one time here, and then tau 2 time into the second medium. Okay? So tau 1 plus tau 2 would be equal to tau. Okay? And this would be V1 to tau. So you would have different wavelets here. Or if I take this one, then it will travel some distance here and then some other distance here. Something like this. So this, in this medium, the second medium, A would have traveled the maximum distance and B would have just started traveling, but just hit it here, and everything else would have traveled some distance which is less than this. And if I do this, if I do all this stuff, and how do you find the next wavefront? The next wavefront would be the tangent common to all these wavelets. So the tangent common to all these wavelets would be this. Okay, so you see, and this is here. Well, so this was A. Now the point which corresponds to A on the new wavefront is this. So notice here, there is a certain bending. It didn't go straight. It didn't go straight. It bent slightly. It looks bent. If this V2 was greater, then what would have happened? Then this would have traveled a longer distance here. Then the tangent would be something like this. In that case, it was bent. It would have seemed to be like this. It would have gone away from the normal. Now it is bending towards the normal. It looks like it's bending towards the normal. It looks like it's bending towards the normal. It doesn't bend. Okay? It's just the wavefront looks like that. But from this point forward, all the points here, all these points would travel the same distance, right? So if we were to draw this one from here, like this, and everything else will be there. And if I draw a common tangent, like this. Okay, so then this will continue like this, and then this will be like this. You see, you can clearly see the ray trying to bend in this, and this is what you see in diffraction when you have a denser medium 2 and a rarer medium 1. The denser medium, the velocity must be smaller, and that is the assumption we have made here. We said v1 is greater than v2, so it will travel a smaller distance here in the given time, the same time. In the given time, the light will travel a longer distance in this medium, the smaller distance in this medium, so it will look like it is bent. That. Okay? So, now this idea is different from the corpuscular theory, which expected, I told you, Descartes said that light will travel faster in the denser medium. No, but we knew that was not the case. Light should travel slower in the denser medium, and only the wave theory explains that properly. So one of the disadvantages of corpuscular theory was removed straight away. Okay, so now let's get to Snell's law. So this is I. Okay, what is Snell's law? Snell's law is sin I by sin R, and we said this must be equal to the ratio. There's a refractive index, and that must be equal to V1 by V2. Velocity in 1 divided by velocity in 2, or speed in V1, and speed in 1 divided by speed in 2. Let's see if I can get to this based on this. Let's see if I can get to this. Okay, this is I. So sin I need to find the substitute, right? Like, okay, sin I can't do much here. Is anything else I here? Well, if you do your geometry properly, then this will be equal to I. Why? So this is 90 degree. Okay, this is 90. This is 90. So what can you expect? And this is also 90. This is also 90, which means that this must be 90 minus I. Okay, and you notice that this is also 90. Wavefront. It's plain wavefront, so 90. So if you remove this I, then this must be 90 minus I, and this must be 90 minus I. This is 90 minus I, and you also know that this is 90, so 90 minus I, this must be I. So this is I and this is I. Using a similar logic, this is R, and you will find this also to be R. Okay, so this is 90 anyway. This is 90. And this is 90. So if you do this stuff, then you will get that this is to be equal to R. The same thing here. So this is R and this is I. Okay, and probably I'll use a different color now. So this is I, and this is R. Now it's easy for me to do sin I by sin. What is my sin I? So sin I is this is 90 clearly, right? It's 90. Sin I is BC divided by AC. BC divided by AC. But what is BC? BC is V1 tau, the time it took, divided by AC. And sine r, again 90, so that's going to be this one. I'll call this as D. AD divided by AC. But what is AD? Well, this was A and B were like A was here when B was here, and in time tau, B traveled to this point, A traveled to this point. So this AD is actually V2 into tau. This velocity of the light in this medium multiplied by the same time. So it's going to be V2 to tau divided by AC. And this is 1 and this is 2. And if I do 1 by 2, is equal, that gives me the refractive index, which is equal to sine I by sine R, and that is equal to V1 tau by AC divided by V2 tau by AC. AC and AC will cancel, tau and tau will cancel, so that is equal to V1 by V2. So refractive index is equal to sine I sine R equal to V1 by V2. So this can be, so Snell's law can be derived from Huygens principle. So even if Snell did not exist, using Huygens principle, you would have arrived at this anyway. So now you know why this is true. Previously, when somebody said mu was sine A by sine R, you just took it at its face value. You just believed it. Now you don't have to believe it, you can prove it. Now you know why sine A by sine R is equal to V1 by V2. And that is actually the refractive index. Clearly, like if it's a rarer medium and it's a denser medium, V1 is going to be greater than V2, so mu is going to be more than 1. So in the case of glass it could be 1.5, in the case of water it could be 1.33, and so on. Hope this is clear. We'll expand on that a little bit. I've redrawn the same picture here. I've removed the clutters, just got the same picture here without the clutter. So this is the incident wavefront. So this point A, the point B. So this is going to act as a secondary source and it will send its wavelets here, and then this will act as another secondary source and it will send its wavelet here, and once it hits here, then it will start sending its own wavelet into the second medium. So this is what it is. So this is equal to I, this is equal to R. BC is V1 to tau. So V1 is the velocity of light in this medium, and V2 is the velocity of light in this medium. This is medium 1 and this is medium 2. Okay, so now you see, look at the wavefront now. Let's see, let me take this. Okay. So this A was here before and this B was there before. Okay, so this is a wavefront. But now let's say that B has travelled here and then A has travelled here. Now this is the wavefront. From that point forward, A would go here and again B, which is equal to C, would come here. So this would be the wavefront. So wavefront is like this. And then come back. It is bent. Now let us suppose that this is the wave length for the wave. Suppose this distance V1 tau is actually the wavelength of this wave here in this medium, lambda 1. So B is here and A is here. So this must be the wavelength of the wave in medium 2, because you notice here, once you hit there, then your A is going to come here and then your B is going to come here. So if I allow the same time, then it will travel the same distance here also, and that same distance will be traveled by this in here. So this will be the wavelength and this should be the wavelength. Okay? So this is the wavelength of this wave in this medium, and this must be the wavelength in this medium. I want you to understand that. So what is the refractive index? Refractive index, we said mu is equal to V1 by V2, which is equal to V1 tau by V2 tau. So V1 tau is BC by AD. Okay. And this is actually equal to lambda 1 by lambda 2. Notice here. So lambda has shrunk here. Okay. So the lambda is gone, and here it has become smaller here. So this was the original wavefront, now this is a new wavefront. So you see, if this is lambda 1, and this must be lambda 2. They are in the same, we're talking about the same points here. So lambda 1 by lambda 2. So what you get is V1 by V2 is equal to lambda 1 by lambda 2. And then I want you to do something else. Let's take V2 there and bring lambda 1 here. So V1 by lambda 1 is equal to V2 by lambda 2. So what is this going to be? V1 by lambda 1. Okay. Suppose you had a frequency F1 here. Okay, and suppose you had a frequency F2 here. So what do we know? V1 is equal to F1 into lambda 1, and then V2 is F2 into lambda 2. That gives you V1 by lambda 1 is actually F1, and V2 by lambda 2 is actually F2. So you see, F1 is equal to F2. So what it means is that when a wave goes from one medium to another medium, its speed may change and its wavelength may change, but the frequency will remain the same. So the frequency does not change. So when you take, say, the light green, it may have a certain frequency in air, and it will have a certain wavelength in air, and it also has a certain velocity c in air. But when you send it through water, the velocity changes and the wavelength changes, but the frequency will remain the same. So the frequency of light green will be the same both in air and in water and in glass and in diamond and in any other medium. The frequency will remain the same, but the wavelength will not remain the same. So the wavelength of green would be something in air and some other thing in water and yet other thing in glass. But in all of them, frequency will be the same. So frequency depends on the oscillator, that's what he said. Speed depends on the medium. The medium cannot change the frequency. If the medium cannot change the frequency, then the wavelength has to change, because this condition has to be obeyed. So in both cases, f is the same. Because v1 and v2 are different, lambda 1 and lambda 2 have to be different. I hope this is clear to you. And that is why I keep saying the speed of a wave depends on the medium, and the frequency depends on the oscillator. It does not depend on the medium. Just because I go into some other medium doesn't mean that the frequency is changed. Okay, I hope that's clear to you. Actually, like if I go into a medium and a different medium, then things could be different, because like the vocal cord, like the pressure, all those things will change. So that's a different story. But if I have an oscillator which produces the same frequency in both mediums, then in one medium it will have a certain wavelength, and in the other medium it will have a different wavelength. That's what I want you to understand.